10.1 Basic Properties of Markov Chains. A transition matrix, P, is a matrix that represents the probability of changing from one of a set number of states to another, including staying in the same state. So over here to the right, you've got an example of a transition matrix. Okay, a lot of times that's called P. I don't suppose it has to be, but that's what they're talking about. A transition matrix is square, meaning 3 by 3, 4 by 4, that kind of thing. It has to be a square. All entries are between 0 and 1, and that's because we're talking about probabilities. These are probabilities after all. The sum of entries in each row is 1. So just keep in mind, when we're talking about transition matrix, we're talking about probabilities, and that's why I used the letter P for probability. Example 1 says, find each probability, and I made up this notation. I don't know that I've ever seen this notation anywhere. I kind of made it up as kind of a shorthand for what to look for. But if you look at this transition matrix over here, what we're talking about is it's like upper class, lower class, middle class, and it's the probability from the probability of changing from one of those to another in a generation. Okay, so let's say you've got parents that are lower class. They're not wealthy, so they're lower class, and they have a child that is middle class. All right, what's the probability of that happening? That's what I'm talking about. Okay, so that first little blank there says probability of going from middle to upper. All right, from M to U means from middle to upper. And so remember, with matrices, we always talk about rows before columns, right? So from middle, so here's middle, to upper is pointing me at this number right here, 0.18. The probability of going from middle to upper in one transition. So sometimes I'll put a little number 1 right there to indicate that it's only one transition. If we were talking about like a great-grandchild or a grandchild, that would be more than one transition. So look at the transition matrix. It says from lower to middle. From lower to middle. Can you see that entry right there? From lower to middle is right here, this one, 0.28. And from upper to lower, anybody want to guess? Upper to lower? Say it again. 0.07. That's from lower to upper. You always do rows first. Lower to upper is 0.7. I'm going from upper to lower. So 0.12. Okay? Good guess. Okay, but we always do the rows before the rows before columns. A transition diagram is a picture of the matrix. And so it says draw a diagram for the transition matrix above. I don't have a whole lot of room here, so let's see if I can do this in this much space. You might want to draw small, okay? If you look at mine, this is what mine looks like, okay? So you can plan that out. There are 3 states in this problem. Either you're lower class, middle class, or upper class. So I'm going to draw 3 circles. One for lower, one for middle, and I'm going to try to draw one for upper and one for upper. Okay? Those are our 3 states in the problem. So you want to look at these probabilities, and you're basically drawing a picture of these probabilities. Okay? So think about it this way. If I'm going from lower to lower, that's just going to loop back to itself, and that's that first number, 0.65. If I'm going from lower to middle, that's 0.28. And from lower to upper, that's 0.07. If I go from middle to lower, that's 0.15. From middle to middle, I don't have very much room here. I'm just going to draw on top of the words. From middle back to itself is 0.67. And from middle to upper is 0.18. Now we look at upper. From upper to lower is 0.12. From upper to middle, 0.36. And from upper back to itself, from upper to upper, is 0.52. So it makes sense. You're just drawing a picture that represents exactly the same thing as the transition matrix. This is a transition diagram. It's just a picture of the matrix. Now we define what a Markov chain is. A sequence of trials in an experiment is a Markov chain if, number one, the outcome of each experiment is one of a set of discrete states. Okay? Two, the outcome of an experiment depends only on the present state. And three, the transition probabilities remain constant from one transition to the next. Number three is an example. A small town has two dry cleaners, Johnson and North Clean. Johnson's manager hopes to increase their market share by advertising. After the ad campaign, it was found that there was a probability of 0.8 that a Johnson customer will bring their next batch of clothes to Johnson. Further, it was found that there is a probability of 0.35 that a North Clean customer will switch to Johnson for the next batch. So we want to give a transition matrix and a transition diagram. So I'm not sure which is easier to see, the matrix or the diagram. Probably, for me, it's the matrix, but maybe since we're just starting, maybe let's look at the diagram first. There's only two states, okay? Two dry cleaners, two states, Johnson and North Clean. So let's do our diagram first. What gets confusing for people is there doesn't seem to be enough numbers. They don't see enough numbers here. So it says there's a probability of 0.8 that a Johnson customer will bring their next batch of clothes to Johnson. So that's from Johnson back to itself is 0.8. It was found that there is a probability of 0.35 that a North Clean customer will switch to Johnson. So from North Clean to Johnson is 0.35. Now, if you think about it, there are a couple of things that are not said, but are implied in that, okay? So that's all the information that was given. The rest of this you're going to have to think about and figure out in your brain, which isn't hard. Let's look at the matrix. I'd rather look at the matrix. So let's call it P. P equals, and if you think about it, we've got two states, Johnson and North Clean. And I'm going to put Johnson and North Clean across the top here. Okay. So what they said was from Johnson to Johnson was 0.8. And from North Clean to Johnson was 0.35. Now, in order to fill out the rest of this matrix, all you have to do is remember what was defined in one of the first slides, okay? We're talking about probabilities, and all the numbers have to be between 0 and 1, but also the sum of the row, everything's going to total up to 1, okay? So that 0.8 represents an 80% probability that they return to Johnson, from Johnson to Johnson. Does anybody know what that implies? It would imply that there's a 20% chance of going to the other, okay? 0.8 plus 0.2 equals 1. That's not given in the problem, but it's also not that hard to figure out, okay? If there's an 80% chance that a Johnson customer returns to Johnson, that automatically implies there's a 20% chance that they don't, okay? And so I can draw this arrow over here from Johnson to North Clean at 0.2. So then look at the North Clean customer. From North Clean to Johnson was a 35% chance. That means from North Clean back to North Clean is a 65% chance. You know this because those numbers in that row have to add up to 1. So from North Clean back to itself is 0.65. So there we've got a transition matrix and a transition diagram. Continued, this one says, North Clean had 128 customers drop off a batch of clothes this week. Use a tree diagram to show how many of those customers North Clean can expect will return for their second and third batch of clothes. Okay, so this seems like it's going to be tough, but it says use a tree diagram. So let's do that. They're starting us off with saying that it's North Clean customers. So at the very beginning, we know they're at North Clean. And specifically, we know there are 128 customers at North Clean. But think about what a tree diagram does. It splits off and shows you all the different possibilities. So what a tree diagram is going to show me is that this North Clean customer can either take their next batch to Johnson or their next batch to North Clean, correct? So think about the probabilities of that happening, okay? Remember, the transition matrix was, what was it? It was Johnson and North Clean and Johnson and North Clean. It was 0.8, 0.2, 0.35, 0.65, right? That was your transition matrix, right? So from North Clean to Johnson was a 0.35 probability, and from North Clean to North Clean was a 0.65. Okay? So that represents the second batch. Okay? That's the second batch. Now, the third batch they're talking about, think about what could happen. From this circle at Johnson, they could either go to Johnson again, or they could go to North Clean. From Johnson to Johnson, according to the transition matrix, is 0.8, and from Johnson to North Clean is 0.2. Down here at North Clean, they could take their next batch, their third batch, to Johnson. North Clean to Johnson was 0.35, or back to North Clean, 0.65. So there's my tree diagram. Apologize for my handwriting, but there it is. It says to show how many of those customers North Clean can expect will return for their second and third batch of clothes. Okay, so return. So we want to know who ends up at North Clean, right? So return for their second batch, we're looking at right here. Okay, so remember, we started off with 128 customers, but it says there's a 65% chance that a customer will return according to this transition matrix, right? And so what we want to do basically is take 65% of 128. That's how many are going to be there. So on your calculator, you can just go 128 times 0.65 and figure out that it's about 83. Okay? So the answer to that first question, second batch, is 83. Now we want to talk about the third batch. Okay, third batch. The third batch returning to North Clean, notice that there are two different circles that we would have to look at. Okay? Remember, they started at North Clean, and we want to know how many end up at North Clean. Okay, so essentially we have to follow two different paths. We've got 128 times 0.35 times 0.2, and we've got 128 times 0.65 times 0.65. We've got to follow both of those paths to see how many will end up back after the third batch. Okay, so 128 times 0.35 times 0.2. That's about 9 people. So that's about 9 right there. And then the other path, 128 times 0.65 times 0.65, is about 54. So for the third batch, I'd add those two numbers. 9 plus 54 is 63. How many will return to North Clean for their second batch? 83. How many will return to North Clean for their third batch? 63.